All right. Did you log in? Send me the code. Let me tell you the code. Chrome. Oh, come on. Hit a search for my friends. Login code 955-388. 388. All right. Then you should be able to block the users and whatnot. And if I'm presenting the wrong thing, you could switch what it's presenting. You don't have it. So if you want to like switch it, you need just to allow that. It doesn't matter. Yeah, I think you have to put a name, but you don't have to add yourself to the stream, so it's fine. So you can, if you wanted to just show, the camera, just switch this one to solo. Oh, that's you. Sorry. Switch this one to solo. Click the guy. So, all right.
That's the only one shot.
Yeah, or you can click like this one.
This one.
Yeah. It'll show the camera and the screen share. Except it's not showing anything on the screen share. I must not have finished.
Okay.
Oh yeah, I have to actually tell it to share the screen. Now it's showing it, right? Okay. All right. We are live. You can stay 6 feet back, okay? I'll get a pool noodle and glue it to my head. Keep everybody 6 feet back. Back in the early days of COVID, I saw a guy walking around a Home Depot with pool noodles stuck on his hat. It was pretty funny. Clearly on purpose to make a joke out of it. All right. You might need to mute your microphone, your speaker rather. I have muted mine. It might. Is it coming out of the ceiling? Hello. Room control. I can turn on the projector. I can move the screen. I can't mute the audio. Mute. Hello, hello. Got it. So years ago, I was asked by my boss to be in charge of a project here at WPI, and the project. It was the way the funding organization was spreading the money around through the different participants in the grant. Our job here at WPI was to spend $1 million. We didn't get to choose the stuff we bought, well, a little bit. But our job was really to go to the meetings where the big whole group decided what it is you're going to buy, and then issue the purchase order. And so my boss was on the grant, and he was bored with that because that's not really research, right? So he told me I had to do it, and it was kind of a cool thing. It was funded by the Army, and what they wanted to be able to do was, let's say you've been flying your helicopter around, and let's say the transmission housing is damaged somehow. Maybe it's just worn out. Maybe flew too close to the desert, sand got in there, it wore out too fast. Maybe it got some damage from an impact. They'd like to be able to as quickly as possible, get that helicopter back in the air, right? They don't like the helicopter sitting on the ground is just a target, but it's up in the air, it's doing something useful. So they want to quickly be able to repair that because it's way faster to repair that cable. And you put it in a machine tool and you'd machine it back to the shape that it needed to be. And often it's like where bearings and bushings go through. And so they, as vibrations go up, those wobble and the hole gets bigger. And then the more the hole gets bigger, the more they wobble and the worse it gets. And finally something breaks. So they try to catch those things before they break. And so you'd fill it in with weld, machine it flat, drill a new hole, put a new bushing in. That's sort of typically the process for that kind of repair. And they wanted to automate that process. What they wanted to do was they wanted to be able to take whatever it was that was broken. At the end of the project, one of the things that we had to be able to handle was periscopes from submarines. Not the same size and shape as a transmission housing for a helicopter. But anyways, that's, what do they call that? Scope creep? All projects have scope creep, right? So anyway, what they want to be able to do is take the broken thing, put it in a machine, press start, walk away. Come back later and magically have the thing be functional, be finished, right? And so, I mean, we know what the process is, right? You fill in the hole. So they weren't using a traditional welding process to fill in the hole. They were using the cold spray process where you take metal powder, you heat it up to almost melting, but not quite. That's what makes it cold. It's almost melting. And then you throw it really hard at the surface and it sticks. They use different gases. The thing we were actually buying, they use, with certain materials, you got to use different gases. Otherwise, like if there's oxygen in the thing, it'll oxidize the material. It doesn't stick. And the materials they were using, they had to use helium to push it. I don't know if you know this, but helium is sort of a non-renewable resource. And if you let go of it, it floats up pretty fast. So what we were doing was we were building a helium reclamation system to go around the system that was doing all that repair work. So my part of it was just buy the helium reclamation parts. And by the way, that was just over $1 million for a space about half the size of this room, maybe a little bit taller with the equipment inside it. And it could capture about 80, 90% of the helium. That was pretty cool. And it regularly did that. Our part of the project worked. But here's the thing. So in order to do this, and they wanted it to be able to take different kinds of parts. So in order to make this work, you had to put the part in, and the system had to say, oh, I know what this part is. Look it up in its database, right? So it's automation. So it recognizes the thing. We talked about this last week. We're talking about when you've got your design and you drag and drop it into the code generating automation system, it's got to recognize what kind of part it is, right? So the system has to recognize what it is, know what's wrong with it, so then it has to scan it, right? And so what they were thinking was laser scanning systems, and they've got these things, right? You can see them, and there's long range ones where you can scan the shape of a car, and then there's close range ones that we have here at WPI where you can actually see how the surface roughness is and how all the sharpness of all the corners are. So some combination of a system like that could scan the part, identify what was wrong with it, then program the cold spray system to go fill in the material, then program the CNC machine to machine. All this had to be in one machine, right? Or you had to move the part back and forth on a conveyor system. We went with a combination of conveyor and one machine. So move it into the CNC machine tool, machine it to the right specifications, and then check it. Maybe do a little bit more cold spray, maybe do a little bit more machining, and iterate on that process till it works, and then do a final inspection, declare it finished. So they want to automate this whole thing. I suggested at one of the early meetings, can we do each of the individual steps without putting them all together yet? So it turns out that just that whole part of scanning the part and finding the damage, that's hard. That might, I mean, if you know what the part's supposed to look like and you know what part it is and you know where the damage likely is, you can probably figure it out. But that's not just, you don't just go to Walmart and buy that system, right? That's not an off-the-shelf system. That's a custom-built system. I told him for doing that part of it alone, if they asked me to do it, it was probably a $10 million project. But they had, like $1 million budget left to put the whole thing together once we bought the helium reclamation thing, and they had to buy the machine tools and all that stuff. So anyways, I tell that story partly because I think it's a cool story and I'm the hero, so it makes me feel good. But mostly because what I want to do is we're talking about automating CNC programming. And that we spent last week, today we were going to move on to a new topic, but I said last week I want to continue this discussion because I think it is something that most of the people in the class were looking forward to. It's based on conversations and stuff like that after we did our little quiz at the beginning. And I feel like we have a need to step back a little bit to make sure we can do all the systems independently before we try to do all the automation and make them happen by themselves. So I told this story also to segue into stepping back a little bit into this CNC programming stuff. First off, rather than trying to work with our individual groups, because I don't know, who's here from group 1? Yeah, who's here from group 2? Who's here representing? Who's here from group 3? Group 4? You guys, you're missing, but you're still missing 2 people, right? And group 5 then is, and you have an outcast. It's an outlier in the back corner. Yeah, instead of doing that, let's group up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 groups of 3. Just group yourselves in groups of 3 here. If you are online and watching from home, really? You blocked him again? So last time this happened, I was live on Facebook and on YouTube. So I didn't do the Facebook this time because I thought it must have been coming from Facebook. Man. All right. You're on top of it though. If you're at home, work on this on your own instead of with the group, unless you guys want to Zoom up together in a group. I don't care. But let's group up in groups of 3. You can move your chairs around, get comfy. And the first thing I want to do in your groups of 3 is make a list of the steps the programmer needs to do in order to write a program. And let's just say that it's for a part that looks sort of like this. So it's a 2D part. So there's, it's a 3-dimensional part, right? Because it's in the physical world. But you can machine it just with top-down machining operations. So the part looks like this here. It's got some outside corners. It's got some inside corners. So write down in your groups of 3. So like move so that you're in groups of 3 so I know what groups they are. Become little amoebas of 3 people. That way I know that you've heard me say that. All right, thank you. And so make a list of the steps the programmer needs to do in order once they've got a drawing of the part. Okay? So the steps you need to do as the programmer in the order that you would have to do them once you have a part, and make a list. And let's take, what do you think, 5 minutes? Let's take 5 minutes to do that. So if you're at home, do the same thing, but you don't get the benefit of a group. Unless you guys want to Zoom each other, I don't care. All right. I guess to conform. The sharing the love, huh? There must be a subscriber. Thanks for the subscriber count. No, I think they just search for live at any moment. Pretty sure.
I think it's a bot.
So the steps the programmer needs to take to make the program. So I heard somebody talking about fixturing over here. And so, yeah, you need to understand how you're going to hold on to the part when you're doing it. But you're not going to spend a lot of time at this step probably, because this is a pretty simple part, right? It's prismatic. So you're going to hold it in a vise of some sort or clamp it down or some sort. So don't spend a lot of time figuring out the fixturing, but yeah. It's in order to make the code, what I'm talking about, what steps you have to take to make the code. So you do have to understand how it's going to be fixtured, but what you really need to do is make the contour around it.
So before you do that, you have to we know the contour shape, but we need to know calculate. Yeah, I'm trying to
like ban
picture in my head and
accounts. All I can do is just block them for 5 minutes.
That's what the block does, is 5 minutes.
Yeah.
Um,
Or I can remove posts. But like, you gotta be rid of ban.
I think YouTube has to ban them. So just report it to YouTube.
well, I guess basically select the line or something.
I'm feeling the love, though. First time that ever happened to me was last week in this class. The other thing that happened to me last week for the first time was somebody made a fake Facebook account pretending to be me reaching out to people in my group.
In your like faculty or
Yeah, somebody made a fake Facebook account with my name, with a picture that's stolen from my Facebook account, and then was messaging people that are my customers.
really?
Yeah. It was caught pretty fast.
Yeah, but still.
First time ever, though. That happens to famous people.
Yeah, I was gonna say, were you like a little bit
I was pretty psyched. I was like, oh, I'm getting famous.
Someone wants to be me.
Well, someone thinks the people that I have as customers on Facebook are worth selling to. That must be. Or worth scamming. I don't know about selling to. I get a pretty quick notice from one of the guys who, yeah. G4, yeah, we're going to talk about that stuff in detail, but G43 is what tells it how long the tool is, or what tells it to look up how long the tool is. Yeah, I'm not expecting you guys to know all the G codes right now, but we're going to talk about that as we go through. So I said 5 minutes, but I didn't actually pay attention to what time it was when I said 5 minutes. You guys ready? Think you know what the steps you have to do to make this program? All right, let's go ahead and move on then. So, unmicrophone the plug. All right, so group over here in the corner. What do you guys want to do? Let me put the screen up. Room control. Screen up. And let's go to. All right, so what do you guys want to do in order to make the program? Check it out, I brought whiteboard markers. I got blue for the white background because it says you learn faster that way. What do you guys want?
So first, acquire a three-dimensional model for that drawing.
All right, so you need the model. Except that one doesn't work. Maybe this blue one works. All right, and we have a model. We have a drawing, right? So we know what it looks like. Good. What's next?
Figure stock.
Select the stock.
Set origins.
Set the origin. All right. You guys can pause. Any of the other groups, did they miss anything at the beginning yet? Does this look good at the top? Nobody had anything substantially different in the first 3 steps? All right, so what would you guys do next?
Select like our tooling and program the tooling if they're not in the database.
All right, so select the tool. You guys like that? Okay.
After that, we had calculate speed, feeds, depths cut based on those tooling.
And so it's based on the tooling, but it's also based on the workpiece material, right?
Yeah.
Yeah. This group. Anybody at home, if you've got a different idea, shout out and Hayden will tell me.
Yeah, create chains.
Create chains. All right. What do you guys got? Okay, so yeah, it's identify the feature. I'm gonna be a more generic. In Esprit, we would call it a chain, but it's identify the feature. Features. In this case, it's really only one feature. It's that outside contour, but identify the features. This group.
I guess our next step would be generate our contouring toolpath and figure out how many we have to make.
Create. And how many passes you have to make is going to depend on the stock material. So how much bigger in X and Y the stock is than the part. And then also the speed, feed, depth of cut and the program depth that we need to go to. If we need to go deeper than we can go in one pass, right, then you'll need to have multiple passes vertically. And if we need to remove a lot of material from the outside. It'll be multiple passes coming in. And that's based on stock material and speed, feed, depth of cut. So create tool path, is that right? And so in a spree, this was like make a chain, right? Is that correct? And so when you're doing the stock, there's several different ways in a spree that you could set the stock material. You could, but typically what we do is we set it in the simulation toolbar. If we're doing 3D operations in a spree, you actually have to tell it what the stock is and what the part is that you want it to make. And in turning operations, you actually tell it what the stock is and what the part is. But for a 2D operation like this, we would probably go to the simulation parameters. We would probably say create stock from a block, and we would give it the dimensions, right? All right, so this set origin. Actually, anybody know how to set the origin in a spree? There's two things involved in setting the origin in a spree. Yeah.
You have to like offset your STL and your stock, like move it, like when you import it.
So if you import solid models that represent the stock and the part, then you want to make sure that they're aligned correctly with each other, which actually maybe you have to do before you even set the origin, but you'll be thinking about the origin when you do that, and you might do it relative to the origin you've chosen. So yeah, you have to do that. You have to make sure that your stock and your finished part line up with each other in the CAM software. Just like in the machine tool, when you're setting it up, you have to actually make sure that you put the part and then tell the machine where the part is, right? Or the workpiece. Okay, so you've got to do that. What else do you have to do to set the origin? Yeah.
You copy those, and then you translate, and then you say remove original. And then
So
you can translate in X, Y, and Z.
Yeah, so you can use the copy feature to move them around individually, or you could select both of them and move them at the same time. What else you had your hand up? Right, under edit, there's the part orient option.
And then you select the vertex.
So you can use that part orient feature, and you can select a face or a point or anything like that where two sides come together. You can select that stuff. And I think that's under edit orient part. I think there's also under edit, there's move origin point. And so you can click move origin point, and you can click on a point where you want to put it. So there's several different ways you can do that. Now, the other thing that goes along with the origin, though, is deciding which of the machine tool's inner coordinate systems that you're going to use. So we normally use G54, right? You guys have all done this when you're setting up the machine and you probe and you set G54 as the work offset. But on the Haas machines, you can go 54, 56, 55, 56, 57, 58, 59. And then there's like 100 more options. And they're up, I forget what the G code is for that, but there's up above 100 somewhere is G something, and then you put a P number and you got 99 of those. So yeah.
Why do we use 54?
Because it's the first one. That's all. It's the one that most people default to when they don't have something else to do. But what in a production shop, or if you've got two different setups going in the same machine, so you might have two vices in the machine, and you're making the top of the part here and the bottom of the part here. And so you make a top, and you make a bottom, you take this out, it's finished, you flip this one over, you put in a new piece of stock, right? So you may have two machines running, and so this might be G54, this might be G55, so that you can write each program individually and you can run each program uniquely. You don't have to put both parts in to run it. You can just run one part, set that one part. But the reason we pick 54 is because we're lazy. But so you've got to, and so in a spree, in the project manager, the properties window, in the properties window in a spree, up in the upper left-hand corner of the properties window, there's a little XYZ. You guys seen that? If you click on that XYZ, it allows you to specify which coordinate system you want to use. I think it's G10, I forget what the 100, it doesn't matter. Here's what I know about G-code. The ones that you need to use regularly, you will memorize. And the rest of them, you don't need to memorize ever, even if you're a G-code programmer. You have to know that that thing exists, or you have to think that maybe that thing exists, right? And then what do? You look it up in a manual. You go look at the list of G-codes and you say, oh, I remember there's one that will pause, right? Because you might get to the bottom of the hole. Say you're drilling a hole. You get to the bottom of the hole. You might want to let that drill sit there for just an instant to help pull the chips up out of the hole, so the chips come up the flute. Especially maybe you got the pressurized coolant going down through the drill. So you got a through spindle drill, through coolant drill. You might want to just pause dwell at the bottom of the hole to make sure that you've cleaned up that hole. So I know that there's a command that lets me dwell, but I forget which one it is. Then you go to the list and you look up which command lets you, or I usually just Google it. Google, but make sure you specify what machine tool you're using if you're Googling it. Not all machines use the same G codes for the same things. I've seen machines where MO3 starts the spindle clockwise, and I've seen machines where MO3 starts the spindle counterclockwise. That's a big difference. So, but yeah, you set that origin, so you decide which origin am I going to use, and then you make sure that your stock and your workpiece is lined up relative to that origin where you want it to be. All right, select, so we select the tools, or we make sure we have the right tools in there. That's in the tools tab in the project manager and stuff. Speed, feed, depth of cut comes in actually when we create the toolpath, right? So we have to know about it, but we don't use it until we get down here to creating the toolpath. And so when we create the toolpath, we go to the operations, either milling or turning operations little toolbar thing, right? And we say we're going to create the toolpath. And so for this operation here, which toolpath thing are you going to use? Because we got a whole bunch, right? There's facing, there's pocketing, there's drilling, there's spiraling, and then there's all the 3D ones. And there's contouring, right? So which one are we going to use? The contouring one, because we want the tool to contour around the outside edge. So if we're doing a contour, anybody have anything after this? Create the toolpath. Was create the toolpath the last thing on your list of things to do? And anybody at home have anything other than create the toolpath? If you did, speak now or forever hold your peace. Okay, but create the toolpath is like, it's not magic, right? So when we get into creating the toolpath, get back to your group now, or if you're at home, stay alone. Get back to your group and describe all of the things the tool needs to do. So describe the activity of the tool in making this part. I'll put the screen down again so you guys can see the part better. But yeah, I agree. These are the getting started steps. These are the things that you as the programmer have to do. Once you get to this create the toolpath step, so you can ignore the G-code stuff down here. We'll go through the G-code too. But that's not what I want to do. That's what I wanted to do. I can zoom in, right? Whoa. And remember the 3 types of motion that we can do in a machine tool? Beside the 4, we can spin the spindle. That's motion, I suppose. But then the other 2 are linear feed, linear arc, either clockwise or counterclockwise, and rapid. Move as fast as you can from one place to another. So get back in your groups. Let's take 3 to 5 minutes in our groups and make a list of what the tool has to do, and just assume you only one pass. So you don't have to do multiple passes. Assume that we can make one pass. In the problem, and I stole this out of the Haas programming workbook. The problem says that the workpiece is steel, and that we're using somewhere it says we're using a 1/2-inch diameter tool. So group up. Let's take 3 minutes and make a list of everything the tool has to do. Oh, and our origin is here. This upper left-hand corner is our origin on the part. All right. This time I'm looking at the watch, though. 3 to 5 minutes. So it has pretty low charge. So every time I can, I just step back over here and plug it in. I just plugged it in this morning.
I got deep into the wire EDM files on that flash drive. Oh my gosh, there's so much to it. Like it's from Taiwan, I think, the machine.
Yeah.
They have so many preset settings that I was playing around with. You can get that thing cut really fast.
If the material cuts.
I was cutting aluminum, so. But I cut it so fast, and it was like, I think it was like almost 2/10 of an inch a minute. And it didn't have one wire.
How thick?
4 inches an inch of cast. Pretty good.
No, I should switch the. Can you switch it to be just the screen share and solo view?
Yep.
Whatever percent coordinate to still at Y positive order and X And then you got linear or wait.
It's actually just caused
It's a clock.
from the bottom of that first time.
So you add the three at the top of the arc on the arc. So it's a raise and then you go down to the line and negative. Right?
Are you guys doing all right? So you don't have to have all the numbers figured out. It's kind of hard to see. All right, so I started over here last time, right? So I'll start back here this time. What's the first thing a tool has to do? Let me get the screen up. We're gonna climb mill. Okay, so we have to. Maybe I'll mute that for just a second. All right, so the tool has to enter the part. So then what? Wait, is that the first thing everybody's got? Anybody have something else first? Yeah. All right, so rapid to clearance plane. EAR. Clear ants or clear ants? Rapid to clearance plane, enter the part. Anybody have anything else first? Yeah.
We have locate tool and then start spindle.
That's why I left room at the top. I mean, actually, even before you do that, you're going to tell the machine what coordinate system it is. And then you can program these machines to be what they call absolute programming or incremental programming. And that's just a way it outputs the G code. So in an absolute programming, all positions that are referenced in the G code are measured from 0, 0. In incremental mode, all positions are measured from wherever the tool is now. So if it's in incremental and you say X 3.2, it'll move 3.2 positive X from wherever it happens to be when it gets that command. And if you're in absolute and you say X 3.2, it'll move to location 3.2 positive inches from wherever 0 is. So some things you can think would be easier to write the code manually if it's incremental, especially iterative things. It's easier if it's incremental. When I was using Excel to create repetitive code and stuff like that, when I'd made my own CAM software using Microsoft Excel, I often would use incremental. And you can switch back and forth in the middle of a program. It's just a command. So you tell it, and then there's some other generic stuff that goes at the front. But in reality, the first thing the tool has to do is get in the spindle. Then the spindle starts. Then we wrap it to the clearance plane. Then we enter the part. Yeah. Not in the operation of the program. If we're setting up the machine tool, absolutely. But in the operation of the program, the assumption is that the setup person already did that. You're right. So we're the programmers. So we'll tell them which tool to use. And in the program, when we load the tool in the spindle, it's more than just loading the tool in the spindle. We load the tool in the spindle, and then we tell the machine tool to reference the length that we programmed for this tool. Otherwise, it doesn't know where the tip of the tool is. And what's important while we're running the program is moving the tip of the tool through the workpiece, not moving the spindle through the workpiece. In fact, it tends to be important to not move the spindle through the workpiece. And when we do it, we're typically not cutting, we're typically stir processing. I know this from experience. Not all right. Now, every time my spindle has come in contact with the workpiece moved. But I have seen people that had sufficient fixturing, so the workpiece stayed in place when the spindle came in contact. It's better for the spindle if the workpiece flies out. Less likely to break. But anyways, all right. So, why is it? So could we flip the order of these two things? Would the program still work if we flipped the order of these two things? But I would always tell you to start spindle first. Because if you've accidentally screwed up the probing and you're rapiding at a low rapid speed, so we've backed off that rapid speed for the first part, for example, and the tool is spinning and it enters the workpiece material because maybe you screwed up the Z when you did the probing, the tool has a chance to survive. If it's not spinning and it comes in contact with the workpiece material, the tool breaks every single time. In fact, if you're handle jogging it to do setting offsets and you accidentally jog it into the workpiece material, just at the smallest jog increment, the tool breaks every single time. And when I look at the tool, I will know how you broke it. Because it's a very distinctive break when you jog down into the part. It chips off the corner of the flute and it spirals up as it chips off. Seen it many, many times. All right, so start the spindle, then move here. You may turn on the coolant if you're going to use coolant. This is a steel part. We're doing one contour around the outside. You don't need coolant. If you get the feed speed and depth of cut right, those chips will turn blue. They might even glow red for an instant, but all the heat goes away in the chip on a steel part cutting like that. So if it's an aluminum part, you probably don't need coolant either, just doing one contour around the outside. You might turn on the coolant to blow the chips away from the part, stuff like that. But anyway, but this would be where you'd turn on the coolant also. You get to that clearance plane, you turn the coolant on there. Sometimes I turn the coolant on right after I start the spindle before I wrap into the clearance plane. That's on machines that I know have a bad check valve in the coolant system. Because if there's a bad check valve in the coolant system, when you turn the coolant off, it all drains back into the tank through the hose. And then when you turn the coolant on, it takes a while to pressurize the system and start spraying out. So if I know there's a bad check valve in the coolant system, I'll turn the coolant on up here. But that's just because we have old machines. All right, what's next? Start the spindle, enter the part. So you got to enter the part two ways, right? You got to come down into the part and then sideways into the part. We'll just call that one thing for now. There's two motions. What do we do next? Do I need the screen up there, or can you guys remember what it looks like? Here, I'll draw it over here. Part looks like this. And I've done this example before. And the tool is here. Everybody remember the dimensions? Yeah.
4x4 and all the marks are
Is
radius 5.
this 4? Is that right?
Yeah.
Okay. And and 0.5, not a capital R, a little r, 0.5, and that's typical. Right, is that good? All right, so our tool is here. Right? That's what you wanted to enter the part? Because we've entered the part. What do we do next? Yeah. What's Kyle say?
Move straight along the top of the part.
Move along the top. Kyle's proven that he's paying attention. Move along the top of the part. Until where?
To the beginning of the corner.
My tool's here. What's next? Yeah.
A clockwise arc. The end of it, the end of the arc. I don't know how to say without. There. Yeah.
All right. Is this on the camera? Reach that far?
Just at the edge.
No, it actually moved it.
Years ago. That's worse.
Yeah.
Do a clockwise rotation.
When I first started doing videos of my lectures, it was before they had all the echo capture and stuff like that. And so I would get there a little bit early, and I had a nice video camera, and I would set it up on a tripod in the back of the room. And then I actually had a Bluetooth mic that would talk to it and stuff. And that was fun. But it didn't follow me as I moved around. And so one term, I hired a kid. And he had a degree. He had a bachelor's in arts from one of those artsy schools in cinematography. And he had worked in Hollywood for 6 years as a production assistant on movies and TV shows. He knew how to do this, right? And so he had the camera, and he had me all mic'd up, and he would walk around during the lectures, right? It was so cool. I mean, talk about vanity points for the narcissist, right? Anyways, Jim was a lot of fun. But that was like made my day. It was like I was Tony Robbins up on the stage, and the camera crews were following me around or something. All right, back to this, right? Yeah.
I always kind of get confused with this, but what's the difference between conventional and climb?
Yeah, when you asked, I was gonna bring that up, and then I forgot, so it's a good thing. All right, so what direction are we gonna spin the spindle here? Yeah.
Wouldn't it depend on the direction of the fluids?
It would, but all the tools that we have here in Washburn, what direction are we gonna spin the spindle? Clockwise. Okay, so we're spinning, and that's this way. Is that true? Okay. Just making sure I'm not backwards. I might be inverted. So we're spinning the tool this way. Right? If we're climb milling, the rotation of the tool is tending to pull us forward along the path. So it's climbing along the path. And we're conventional milling, we would take the same tool, same rotation, but we would go this way. And the rotation of the tool would tend to be pushing back against us. The reason in manual milling, where you're doing it etch-a-sketch style, you're turning a handle to control the motion. The reason we typically do conventional milling there is because then it adds to how much force we have to put into the handle as we're feeding into the part. And we get sort of a more constant pressure of the workpiece pushing on the tool, right? Because the workpiece deflects, the tool deflects. And if it's pushing back against us, it won't get away from us. We've got to put a little bit more effort into it to make it go forward. Whereas with climb milling, the cutting force could want to pull the tool forward, and it could actually get away from us. I mean, it won't like go crazy and fly across the room probably, because there's a lot of mechanical advantage in the screws. But it could tend to get away from us. But if you've got a rigid system, this always makes a better surface finish. It always makes a nicer part, usually. Always usually. That's a thing, right? There's certain materials, certain tools where this makes a better part. But it tends to be more efficient. And in a CNC machine tool, you've got thousands of pounds of thrust available from the servo motors, and they're fighting that effort of it pulling forward. So that's why we'll always do climb milling in a CNC machine, pretty much always, unless something special. All right, so we're here. Now what? Yeah.
You linear feed to the start of the next arc.
Here. Now what? We got a system, right? Now what? Yeah.
Linear feed to this. Wait, what size tool are we using?
Half inch.
Half inch. So linear feed to the center point of the next arc.
So if I stop here, can I stop there? I actually can stop there, but it's a more complicated tool path, right? If I stopped here, I could make a small arc such that that stays in the same place the whole time, right? And the tool moves around. But typically what we would do is come over to here, stop here, then feed in a straight line to here, and then make the arc around. Does that make sense? There's a couple different ways the tool could go through this, but this is typically what we do. And then feed out, and then feed up to here. Once I get here, I need to feed off the part, then I can come up, then I can go to the tool change position or whatever I want to do with the tool, right? So if you're programming manually with G-code, get this thing back on. Ah, wrong page. If you were to write this code manually with G code, so remember I told you, so T1, MO6, tool 1, MO6, put the tool in the spindle. So operate the tool changer. G90, G54, G00, this G90 tells it we're going to use that. I told you about the absolute and incremental. That tells us we're going to be absolute. G54 tells us, hey, we're going to use work offset G54. G00 is rapid. We're going to move from wherever, well, in this case, we know where the hell we are, right? We're at the tool change location because we just changed tools. We're going to move from the tool change location to the start point. And the start point has an X and a Y, or the, I guess it's not really the start finish because it's above the start finish, right? The clearance plane at the start point. Then, and so, oh, XY, so it's still high. So it moved an XY before they turned the spindle on. I totally would have turned the spindle on first. Then it's going to rapid, so this G43H1Z.1. So it remembers that we're in G00. It remembers that we're in rapid. As long as I don't give it a G01, G02, or G03 command, it will stay in rapid. And every X, Y, Z location I give it will move in rapid to that location. So here I've given it a Z after G43H01. The G43H01 says, go to the memory register in the machine tool, G43, go to register H01, H is associated with T. So the length register, the height register for tool 1. We could put H22 there. And it would then go to the tool register and look up the length that we associated with tool 22. There is a thing in the Haas controller where you can say, throw an alarm message if the H and the T don't match. But that's what the G code here is telling it. It's so if you wrote this code manually and you left out the G43, it would drive the spindle into the workpiece, not the tool. Well, the tool might pass through on the way, but it would drive the spindle into the workpiece if you left out this G43H01. Also, if you said H22 here, but then you didn't set a length in memory register number 22, then it would drive the spindle into the workpiece. So those are things. You're not going to have to typically do this. I don't ask students to write G code manually. In fact, I ask students to not write G code manually. It's a couple reasons. It makes it hard to simulate in the CAM software. But I guess even if you did write G code manually, then what is the CAM software? No, it's your head. It's your gray matter. So maybe in some people's cases, it's useless. Right, so and what's the purpose of simulating the CAM software in our safety steps? Because it's required, it's one of the 6 required safety steps. What's the purpose? Yeah, so it could show some potential crashes. But the real function of simulating the CAM software, assuming it doesn't crash, so assuming that we wrote the program correctly and we checked for crashes before, when we're at the machine tool, I want you to simulate in the CAM software again. It's so that you, in your mind, know what the toolpath is supposed to look like. That way, if it does something different inside the machine, you have some basis to hit the e-stop. Right? That's why that step is in the at the machine safety protocol, is so that you know what so if you wrote the code manually, or if you can read the code and know what it does, then your mind is simulating in the CAM software because the purpose is for you to know what it's supposed to look like. Anyways, so you'll see these things. And so if you're troubleshooting a program, and this happens a lot, if you got tool 1 and you come down and you check the distance to go and you see it's going to crash, so you reset the tools. You measure the tools again, and you measure the workpiece again, and you start again, and you check the distance to go, and it still looks like it's going to crash. You can go to the G code, and you can say, all right, does the H and the T number match for that spot? Because it's possible in the CAM software to accidentally tell it to use a different offset register. And so if you're troubleshooting a program, that's a thing that can come up, is do the H and the T match? And if they're different, is it on purpose? When would you ever have the H and the T be different on purpose? I can think of 2 instances where it would be a very beneficial thing to change the H and the T, have them not be the same. So one would be, what if you had a chamfer tool that had a chamfer on the top and a chamfer on the bottom? So it's like the shape of the tool. Who designs a classroom where you can either use the projector or the whiteboard, but not both? Clearly somebody who has not taught in a classroom using wrong button. That's the button. If my tool looked like this, it would probably be more symmetrical. But if this is a cutting edge and this is a cutting edge, I could use this cutting edge to put a chamfer on the top of my workpiece. And I could use this cutting edge to put a chamfer on the bottom of my workpiece as long as it hangs out and I don't run into the fixturing when I do that, right? So with the same tool, I could do this and I could do this. Now, maybe I have some variations in thickness of my stock material. And so one quick way to change the size of the chamfer is to change how high the tool is, right? And so I may need to dial in the chamfers separate from each other if I've got some variations in the thickness of the stock material. And so I may set this to be H1 and this to be H11. And then at the machine tool controller, I could make a part and say, oh, the top chamfer, or the bottom chamfer is too small, so I can reduce the value for that H11, bring the tool up a little bit, and then run the part again. It'll redo that without affecting the height set for the other one. So that's one reason you might have two different H values for the same tool. The other reason would be, well, no, it's the same reason. Never mind. There's only one reason. But it wouldn't have to necessarily be a chamfer tool. If you were doing two different pockets, or you had a pocket and a boss on the same part, and for whatever reason you needed to adjust the height of the boss separately from the depth of the pocket, and you make both features with the same tool, you could associate a different H value for the different operations. And so you could adjust those two features separately. And that's for dialing in production parts, things like that. So we wouldn't do it often. We probably wouldn't do it in an automation scenario, unless maybe we were automating the repair of housings for helicopters. But I suggested that what they really needed was a skilled operator and not an automation system. But in getting approval for the budget from Congress, they had told the congressman that they were going to have a fully automated system. Therefore, we couldn't rely on a skilled operator. In reality, they wanted to be able to drop these things out of the back of a C-17 and start making parts same day. That would be cool. Think how cool that would be, actually. If you could have something the size of like a small tractor trailer and just show up somewhere and put in raw material and press a button and have your parts come out. It'd be like a taco truck that made stuff. That would be totally cool. Because you drive it to where you need it, get the raw material to meet you there. In the meantime, FedEx delivers overnight. Back to this. Where was I? Over here. Screen down. Mute off. At least we've got automation in the rooms, huh? All right, so we've got the tool and the spindle. We wrap it down. So here we do our G01. We do G01 F50, 50 inches a minute. I would probably not do 50 inches a minute here, but they wanted to save time. So they wanted to quickly get to the cutting position. And they knew that they weren't going to encounter material when they did that step. So they did this Z whatever, they're going to negative 0.65 or something like that, I think, in the program statement. At F50, all right, if you know that you're not going to encounter the material and you want to move fast, then you might as well stay in rapid move, right? But whatever. Some people like to have a fast feed, right? It's even called fast feed down to the depth. I would either rapid or not, but that's me. So here we've switched to G01 though. So we know that we're doing linear motion. And so all of the X, Y commands from here, it's going to do a linear motion at feed 50, except on this one, we told it to slow down to feed 12. So it's going to 12 inches a minute instead of 50 inches a minute to move sideways through the workpiece at 1,520 RPM 1/2-inch tool. And so that's typical feed speed depth of cut for a steel part here. And then here it's going, so this X here would be the end of that first straight line motion, right? And then the XY here is the XY coordinate for the end of that first arc. R is the radius of the arc. So it's going to move from the point that it ended up here to this point along this radius. Does that make sense to you guys? Anybody know what the radius is? 0.5? Who votes for 0.5? Be proud. Have an opinion. Who votes for something other than 0.5? Anybody? Like 0.49, 4968? Anybody? Anybody? Why did you pick 0.5? Oh, you want to change your vote now?
I do.
How many people do you think? Oh, never mind. I'm not going to bring up politics. I was looking this weekend. I was looking up a machine shop, and the website was pretty old, like vintage vintage like 2012 or so. And you can tell by looking at these websites that they're pretty old. And I actually knew that the owner was 80 years old. And I'm wondering, I wonder if it's still open. Because what if you just bought like 10 years of web hosting and you put up your website and you close your business? Are you going to remember to go shut down the web page? Probably not. I've closed a business and left the web page up for 3 years after I closed the business, even though I was paying for it. At first, it was because I didn't want anyone to know that I closed the business. Right? That's just like if I put down the web page, then people will know that I closed. Right? Not customers. The customers all knew. It was like my friends. Right? I didn't want my friends to know. Anyway, so I went to Google Street View. Like, I could have driven over there, but it was like 50 miles away. So I go to Google Street View and I was like, hey, this image is from summer of 2021. That's pretty recent. And they were hiring at that time because they had a sign out front that says they were hiring a machinist. So that tells me that they probably still existed in August of 21. There's a big flag in the picture. It says, don't blame me. I voted for Trump. I'm just like, I don't know. So I'm not going to talk to the guy about politics when I call him up. but I guess the company still exists. So you wanted to change your vote. That's what do you change your vote to? 0.75, because it's the radius on the part plus half the diameter of the tool, because we're programming for the center point of the tool. Right? Now there's a way to program for the edge of the tool. And if we had that turned on, we would also have to then tell the machine tool how big the tool was in diameter. And then we would have another line of code up here that's a G41 with a D. And so we would do like G41 D1. And then we would, when we set up the tool in the machine tool, we would tell it that it's a 1/2-inch diameter. And the D then would have to be associated with the tool number. And then we could program for just the radius we want to be on the part. But yeah, this just quickly, this I and J, you use it instead of R, not in addition to R. And it's the vector from where the tool starts the arc to the center of the arc. So I is what? X and J is Y. So in this case, the center of the arc is directly below the start point. So I would be 0 and J would be 0.75 negative. So it's just another way to define it. Some arcs are easier to define with I and J. I normally teach this G-code programming to not people that are like within a year of graduating from WPI. So I can't say things like it's the unit vector from that, or it's not the unit vector, it's actually the vector. I can't say that to those people. I have to, it's hard for people that don't understand vector math to know what I mean, but you guys know what I mean, right? Perfect. I was teaching that class. What time I got? All right. When I started teaching that class, the people that were advising me on that class, like, you got to remember, they're not WPI students. And the first class started, and if I had forgotten within a half hour, I knew. But okay, so that is the basis of all, and we could go on through these things, but that, you don't need that, do you? So when I first learned how to program CNC machine tools, I had done a little bit of machining. So you guys know I was a student here. So junior year, I think it was junior year, middle of the year, either B term or C term, sometime around there. I took ME3820 because I wanted to be able to learn to use the shops so that I could make cool stuff. Right? Anybody else ever have that feeling? I want to learn how to do that stuff so I can make cool stuff because I want to make cool stuff. And so at the time, the Washburn 107 was divided up into cubicles. Each cubicle, they were pretty big cubicles, but each cubicle had a workbench and a pegboard. I wish we still had that. With all the tools that you might use while you're in the cubicle. It had a manual milling machine and a manual lathe and a bracket for a TV. There were no TVs, but there was a bracket for a TV. When they built all the cubicles, they had assumed that what they were going to do was they were going to have VCR. This was back in the VHS, maybe Betamax days. They were going to have VCR videos that would teach the students how to do milling and turning on the manual mill, the manual lathe in a cubicle. The machinists that were in charge of the facility knew better. So although the bracket was on the wall, there was no TVs and there were no videos. And because of the cubicle walls, there were nervous machinists running around because they couldn't see everybody all the time, right? So they were making sure that nobody was dying, basically, in the machines. And it was in 2006, shortly after I took over the facility. We'd already, around 2000, we got rid of the cubicle walls. In 2001, we brought in the first CNC machines. Well, not true. There was a CNC machine here when I was a graduate student in the late 1990s. It had been a manual machine. Someone had then added an NC controller to it. So these were like the machines where you fed in it was a tape. Fed in a tape with holes punched in it, and it would have little fingers that would read ones and zeros, and it would then get to the control. And the Z was controlled by a hand crank. You could move it up or down. So the Z was still manual, but it had XY control on it. That was pretty cool. So that was, when I was a grad student here in the 90s, that was the CNC machine we had on campus. And then in 2001, we got all the Haas machines in, and we became a Haas showroom and all that stuff. That was pretty cool. So yeah, I had run the Bridgeport thing. It was a Bridgeport with the NC control on it. I had run that, but only like to crank the handle up and down. Someone else had always done the programming part of it. And the only thing I ever did was do some engraving on some parts. But I had run that. So I suppose I had run a CNC machine before 2001, but not really. Then 2001, we got all the Haas machines. I was a grad student still. And they gave us some free training at their factory outlet. And we had more training slots than we had people that needed to be trained directly. And since I was a manufacturing grad student, they offered me to go to that training. It was pretty cool. So I went there. I'm getting trained by Hawes to learn how to run these CNC machines. Because let me tell you, when I did ME1800 in the early 90s, I did not feel prepared to go in the shop and make cool stuff. I still felt scared, felt like I didn't know anything. And I also didn't especially feel welcome. I wasn't one of the cool kids that had become friends with the machinists. And they hung out with their cool kid friends. And the cool kid friends could come in and make stuff. But I wasn't one of the cool kids. So I didn't feel welcome, and I certainly wasn't competent. But anyway, 2001, I go to the training, and we used probably exactly the same version of the workbook. And we went through that workbook from the first page to the end in 3 days, and we did all these exercises, and we did trig to find out where's the points in the corners and all that stuff, and because the exercises get more complicated as you go in. And I remember about halfway through the second day thinking, I am gonna be so rich, because I could write a computer program that could do all this math for us very easily. And you could take your drawing of your part and you could input it into the computer program, or you could take your solid model of the part, you could input it into the computer program, and it would automatically figure out what all the points are. And you just have to tell it like the feed speed and depth of cut that you wanted to use. I was going to be so rich. We went through 5 days of this training. The guy doing the training never mentioned the existence of CAM software. I mean, by the end of the training, I was flying a Learjet. I had the big Jaguar, the big Mercedes. I was going to be so rich. Yeah. Turns out I wasn't the first person to think of it. You could already buy CAM software back in the 80s. But the guy that did the training at the Hawes factory outlet, he was not a believer. He thought you had to do G-code. In fact, he thought you had to do trig before you did G-code. Not a believer. He still does the training at the same factory outlet. He begrudgingly allows the fact that CAM software exists now, but he still steps you through the hard way. Anyways, I do think we needed to have some background feeling for how the tools move and the things. You're never going to have to memorize. Even if you're doing manual G-code programming, which people still do in industry. I used to do it a lot for simple parts. Sometimes it's actually faster just to write the code than it is to put the model in, find the features, do all those things. However, if you're good at putting the model in, finding the features, aligning the parts, it's probably faster to do it in the CAM software. Yeah. I hope that gives us a better sort of background feeling for the steps that go into this. So we've got Thursday coming up. What's everybody doing for Thursday? Everybody's going to have at least a simulation of at least one of their parts, right? Some people are going to actually have a part, right? Which groups think they're going to have a part? What's your part going to look like?
We haven't decided exactly
Which one, but you're going to try to make a part. How about you guys? What's your part going to be?
I have the cam mostly done for the part we went over in class on Thursday.
Okay.
I'm going to try and make that.
All right. I think what we need to do to make sure the projects are worthwhile is we need to, as quickly as possible, start making parts, even if they're bad parts. I would rather have you guys, even if you're going to have to adjust the design later, because you don't, the puzzle group, you're going to have to figure out how to make all those parts fit together. You may have to make some of the parts several times before you've figured out what the right tolerances are, so you get the right sliding feel on the fit. That's not something you're probably going to look up in the machinery's handbook and know what the right sizes are. I think you're going to have to get a feel for that. But let's, as quickly as possible, make sure that we've got a good part. Let's see, what else? Some general feedback for the for the class on presentations. And maybe this comes from the fact that I was in ROTC when I was in college here, and we had leadership training. And one of the things they did in the leadership training was they stressed on your ability to make presentations, because I guess military officers do a lot of PowerPoint. Actually, it's true. But so maybe it stems from that. But I feel like if I'm going to be the person standing in front of the room doing a presentation, I should probably have pants on. So far, nobody came without their pants on that I noticed, but more than once I saw sweatpants and pajama pants. So I try to, on days that I have class, I try to present myself as if I respect you. That's what it is. I used to always wear a tie. Always would wear a tie when I was teaching. I used to joke about it. I'd say, oh, it's because I'm so young and I don't want the students to think I'm one of them, so I have to dress differently. But no, the real reason was because I actually like wearing ties. But the real reason was to show respect for the class, to show that I was putting some extra effort into it. And so if you could appear to respect the people that are watching you by looking like you put some... a friend of mine, when he did his PhD dissertation defense, he spent a long time deciding what he was going to wear and picking out just the right outfit to wear, because he wanted for himself for this to be a memorable thing, and he wanted to be able to have pictures of himself. The outfit that he chose would have looked cool in a disco, or maybe a hip hop club. Not so much for presenting to the 70-year-old people that have to approve your dissertation. But there's that. I think also, so I think we've got a good 15 minutes scheduled for each group. So think about what you can do so that your presentation starts and finishes. And there's a little bit of time for questions and switching the groups. But you guys have been finishing in like 7 minutes, which is okay, but it's half the time allotted. So you had twice as much time to get feedback from the class, to present the thing. So if there's something that you've been having a lot of trouble with, present the fact that, hey, we're having a lot of trouble figuring this out and we could really use some help on this so we can get some better interactive class discussions. And I really think you guys need to make some parts. I think I am a little bit regretting not doing the first lab the way I used to do the first lab in the class, whereas I gave you a solid model and a drawing, and I said, come back in 2 weeks with a box full of parts. And we were in groups of like 3 or 4 at the time, and each group had to come back in 2 weeks with a box full of parts. And if you didn't know how to use the CAM software, if you didn't know how to get access to the mills and all that stuff, you had to work with the PLAs and figure that out, or the TAs. I kind of wish we did that this term. I didn't do it because I didn't know until the day the class started or the day before the class started that I was going to have TA support, and I certainly couldn't handle 30 people, all of you coming to me not knowing how to do it at that moment. But get in there, make some parts. And we'll take a few minutes on Thursday at the end to review the schedule for the rest of the term and see if we want to make any modifications to our plan, since I already modified the plan this week and we're not doing the thing that was originally scheduled for today. I think you guys want to keep looking at CAM stuff. But we'll talk about that on Thursday. So be thinking about that for the Thursday discussion. I certainly want to make sure that we talk about PLCs and PLC programming and ladder logic. And then some of the other stuff might just be some class discussion instead of getting in depth in that, the robotics and the other automation stuff. But I think the feeling I get from interacting with students in the class is that you want to spend more time on getting better at CAM. And so I think we'll try to concentrate on that. But think about it for Thursdays so we can have a discussion on that topic. Anything else? Any questions from the home people? Any more strippers on there? If you guys, oh, there's somebody that's commenting. There's links and you can go look at unclothed pictures. Online strips without clothing. If they don't have clothing, what are they taking off? That sounds pretty boring, actually. It's not much of a show. I think they need to work on grammar, too. All right. Anyway, I'm done for today, unless you guys have more questions.